So let us look at an example. So it is given that we have two parallel plates and water flows between these two plates. So these plates have infinite width in the z direction. So it is given that the lower plate moves towards the left at a speed of 0.3 meter per second. The plate spacing is 3 millimeter and the flow is laminar. So the question is, what is the pressure gradient? So what is the pressure gradient that must be maintained in this between these two plates, across these two plates rather, in order to have a zero net flow? Okay, in order to have a zero net flow, what is the pressure gradient required? Okay, so in fact, we can make use of the solution that we have done above also. Simply integrate over the area. It doesn't matter if it's going in the negative direction or all that. We can simply attach a coordinate system like this. We can simply attach a coordinate system and this becomes equivalent to whatever we have analyzed so far. But anyway, let us not skip the steps, or let us not do all those kinds of coordinate transforms. We can write down mu d2u dy2 is equal to dp dx, but dp dx we know is going to be a constant. So upon solving this, I'm going to write down the boundary conditions. And at u at y equal to 0, u equal to minus capital U, where capital U is equal to 0.3 meter per second. At y equal to h, so h is basically 3 mm, u is going to be equal to 0. So these are the boundary conditions. So we have du dy is equal to 1 upon mu dp dx times y plus c1, and u equals to 1 upon 2 mu dp dx y square plus c1y plus c2. So using the first boundary condition, so c2, so 0 is equal to minus capital U. So sorry, at y equal to 0, u equal to minus u, so minus u is equal to 0 plus 0 plus c2. So c2 is equal to minus capital U, and using the second boundary condition, 0 is equal to 1 upon 2 mu dp dx h square plus c1h. So c2 is minus u. So from this we obtain c1 equal to u minus 1 upon 2 mu dp dx h square, and there will be a divided by h. So c1 comes out to be u by h minus 1 upon 2 mu dp dx times h. So then if we combine if we use these two constants in the expression for the velocity, so the velocity comes out to be u equal to 1 upon 2 mu dp dx y square plus c1 y. So c1y will become u y upon h minus 1 upon 2 mu dp dx y h plus c2. So c2 is simply minus u. So this is 1 upon 2 mu dp dx y square minus yh plus u y upon h minus u. So now we can integrate this over the entire channel. So this is not the coordinate system. We have used this coordinate system only. So Q is equal to integral U dA. So if we assume the width into the paper as W, so it will be U W dy. So if we assume a unit width, this W can be simply removed. So remember that these calculations are all per unit width. So this integration will be from 0 to h. So what do we have? So it's 1 by 2 dp dx. So this will be y cube by 3 is going from 0 to h. So this will be h cube by 3. This will be y square by 2 times h. So this will be minus h cube by 2 plus u upon h. So y square by 2. So this will be h square by 2 and this will be y. So this will be h. So this is equal to, so this will be equal to 1 upon minus 1 upon 6. So minus 1 upon 12 mu dp dx h cube plus, so this will be uh upon 2 minus uh. So this is minus uh upon 2. So if this flow rate has to be equal to 0, right, then the pressure gradient comes out to be minus of upon 2 times 12 mu upon h cube. Yeah, that's it. So this becomes minus 6 mu u upon h square. So if we plug in the values, so it is minus 6. So time the viscosity of water at 60 degrees Celsius. So the entire problem is mentioned that it is at 60 degrees Celsius. So quite naturally it's for some kind of a journal bearing. So the viscosity is given as 4.7 into 10 to the power minus 4 Newton second per meter square times the velocity is 0.3 upon h square. So the gap is given as 3 millimeter. So it is 3 times 10 to the power minus 3 meter square. Let me just plug in these numbers into my calculator. So this becomes minus 6 times 4.7 times 1 minus 4 0.3 divided by 3e minus 3 squared. So it comes out to be minus 94 Pascal per meter. So essentially it means the pressure gradient is negative, meaning the pressure gradient would act in this direction. Okay, it's a negative pressure gradient. So minus dp dx is essentially 94. So minus dp dx acts in this direction. So the plate being pulled tries to have a velocity profile in this direction, but the pressure gradient tries to have a velocity in this direction. So it would be something like this. Okay, so the volume in the negative direction and the volume in the positive direction would be balanced. Now having said this, if you do have a situation like this, there is no guarantee that the flow will remain stable. Okay, on the one end you have a plate being pulled in this direction, on the other end you are sort of trying to push fluid in the other direction. So it's not always a stable configuration. So this is the direction of minus dp dx, this is the direction of u. So if you have fluid, you can imagine that the fluid is trying to overturn. So the assumption of unidirectional flow, it need not be always maintained and it can lead to a flow instability. So flow instability is something in which you have a flow configuration, but the flow configuration is sort of unstable to certain disturbances. And I say certain disturbances because it is not unstable to all disturbances. It is unstable to disturbances of a certain wavelength or a certain frequency. So if this happens, then the flow will break up into various kinds of secondary flows. It can in fact become turbulent. So one mechanism by which such a kind of counter flow, so this flow is, one flow is being dragged in this direction, one flow is pushed in that direction, so it leads to the formation of a Kelvin Helmholtz instability. And this kind of instability can be seen in the formation of clouds. So there will be such kinds of weird structures. I mean, of course, I'll put the image while uploading, but it leads to something like this. In fact, let me look it up. Let me paste it over here. Yeah. So now that we have the appropriate credit to the author, so this is one example of the Kelvin-Helmholtz instability, in which the flow on the top of these clouds is happening in this direction, but on the bottom of the clouds is happening in this direction. That leads to, so if everything were to be okay, the flow would be simply like this. But because there's a rotationality, it tries to overturn. Okay, it tries to overturn. So these kinds of patterns are found all over the universe. In fact, you can look up the images of the giant storms in Jupiter, on the surface of Jupiter, and you will see such kinds of patterns. So on Jupiter, what really happens? So let me dig up an image of that also. I need to credit the author as well. Yeah. So this image is courtesy ESA, European Space Agency. So you can focus on this. Okay, over here, over here, in fact everywhere, even here. So basically these are parallel layers of fluid in which one fluid is going one direction. So one layer of fluid is going in this direction while the other layer of fluid is trying to go in the other direction. So it leads to a shearing at the interface, and that leads to instabilities. Okay, so this kind of unidirectional flows act as the base. Okay, so these are whatever we have studied so far. So these are also often referred to as base flows. So in base flows, you don't consider this, and then you can perturb a base flow and see how that equation evolves in time. So far we have considered analysis of a plane Poiseuille flow and a couette flow.